Hello, good morning. So today we are discussing about the two compartment open model extravascular. Last class we finished two compartment open model IV infusion. So here we are discussing about the extravascular. So this table you have already discussed. Now in two compartment extravascular we have two different compartments with a rate of absorption as Ka and the rate of distribution from the central compartment to the peripheral compartment as K12 and reverse as K21, and the elimination of the drug from the central compartment at a rate of Ke. Okay, so this is the schematic representation of two compartment open model extravascular administration. So this compartment modeling again is similar to that of the IV infusion to compartment also. The only difference there we had R0, that is rate of administration at a zero order model, and here we have rate of administration follows a first order kinetics, that is Ka. Okay. Now, do you remember how we determined the presentation of drug in central compartment in IV bolus as well as IV infusion? Separately, compartment wise, we determine the presentation. For the central compartment, what is the change in plasma concentration, and for the peripheral compartment, what is the change in plasma concentrations. Now the first question today Sherin can answer. What is the order of the processes here? What is the order of Ka, K12, K21 and Ke? For all these kinetic parameters, all this rate constant happens at which order of the process? Okay. Now the general equation, how to determine the change in plasma drug concentration in the central compartment, that is dx by dt. So dx by dt, that is equal to the amount of drug that enters as matters and amount of drug that eliminate also matters. So here the drug is entering from the stomach into the systemic circulation at a rate of Ka, and it is depends upon the amount of drug present in the stomach, that was Xa. I hope you remember one compartment extravascular administration. Okay, so this is taken from the one compartment extravascular administration, that is the amount of drug that reaches into the central compartment is Kxa. Now the drug is moving from the central to the peripheral on the rate of K1 to XC, K1 to XC, and plus drug is moving from peripheral to the central compartment, that is K21 XP, and minus the drug is eliminating from the central compartment, that is KE XC. So we have four processes. I am repeating, that is Kxa. Equation is this: dx by dt, that is equal to Kxa plus K21 XP minus K12 XC minus KEXC. The XC is the amount of drug in the central compartment, XP is the amount of drug in the peripheral compartment, XA is the amount of drug in the stomach. So this is the general equation for amount of drug that is present or the change in the presentation of drug in the central compartment. So this equation, after integration and after substitution of hybrid constants and micro constant, we will get a one equation. So here luckily you do not have any derivation to learn. The finite equation we have, that is C is equal to L e raised to minus alpha t plus m e raised to minus beta t minus n e raised to minus kat. So here you have three different new terms, that is L, m and n. So where L, m and n are the hybrid constants, L, m, n are the hybrid constants, and alpha, beta and Ka are the alpha and beta are the micro constants. Okay, so the same type of constants you have learned in IV bolus two compartment. There we learn A and B. Capital A and capital B are the hybrid constants we deal there. So this is also same hybrid constant, only the variables are different. Okay, now N is the hybrid constant that representing the process of absorption. M is the hybrid constant that representing the elimination. L is the hybrid constant that representing the distribution. So we have three exponents here, that is distribution, absorption and elimination. L represents the distribution hybrid constant, M represents the elimination hybrid constant, and N represents the absorption hybrid constant. Alpha and beta are the micro constant which are having the same values what we learned in the one compartment IV bolus. Okay, so Roshida, you can answer what is L represents, Roni what is M represents, and Maria Lopez what is N represents. Okay, now so this is the graphical representation of a two compartment extravascular administration. Now you look into this graph. So here we have an absorption phase. Clearly there is absorption happens. Here we have a distribution phase, and here there is an elimination phase. So how can you differentiate this is a one compartment or two compartment? It is based upon the rapid declining in the distribution or rapid declining in the plasma concentration from the peak plasma concentration. When there is a rapid decline in the plasma concentration from the peak plasma concentration, we can identify there is a that follows a two compartment model. Okay, so this graph represents a two compartment extravascular administration. So here we have the general equation. This we have already come across. Now we need to determine the rate constants now, that is absorption, distribution as well as elimination. So this is a tri-exponential graph, or this is an equation representing the three exponents. So in order to determine the each rate constants, you have to apply the method of residuals, and determine each and every rate constants. In the one compartment extravascular, two compartment IV bolus and two compartment IV infusion, we apply the method of residuals in order to split the tri-exponential curve into bi-exponential and a bi-exponential curve into a mono-exponential curve. So the process of determination remains the same that you already come across very well. You know it's exactly how to perform this representations. So this tri-exponential graph representing absorption, distribution as well as elimination. Among these three exponent, one exponent will be lower and two exponents will be a zero value. The two exponents will be a negligible value and one exponent will be a higher value. So what are the two exponents that are zero? Ronnie can answer. What are the two exponents that are zero? Now if you look into the equation, we have we have elimination and we have distribution. So an extravascular, if you consider an extravascular two compartment, absorption will be completing faster as well as distribution also will be completing faster. In the elimination phase, that will be purely what? Purely elimination alone. So that this you can clearly understand from this graph itself, because in this elimination phase, we call this elimination phase ourselves. Why? Means there is only elimination. So the two terms, that is e raised to alpha t representing the distribution and e raised to minus k8 representing the absorption, becomes 0. Finally, what is remaining? C is equal to m e raised to minus beta t. This we call it as the C back extrapolated is equal to m e raised to minus beta t. Okay, so C back extrapolated is equal to m e raised to minus beta t. Taking the logarithm, you will get log C is equal to log m minus beta t divided by 2.303. Log C equal to log m minus beta t divided by 2.303. So this happens only in the elimination phase. So here is the log C back extrapolated is equal to log m minus beta t by 2.303. So here is the graphical representation. If we look into the graph, okay. So the graph with the red line, which represents the general plasma drug concentration. The red one which represents the general plasma drug concentrations. So that one we have back extrapolated from the elimination phase into the y-axis. So that y-intercept represents what? Y-intercept represents the log m, that is capital M. Equation for this line is, that is log C back extrapolated is equal to log C back extrapolated is equal to log m minus beta t divided by 2.303. So this is the equation for this line, that is a back extrapolated line. So now we go to C back extrapolated. So we have a general plasma concentration represented by a red curved line. We have a black extrapolated concentration again representing by a red line, that is back extrapolated to the y-axis and intersected on the y-axis, and the y-intercept is also marked as log m in the red in the y-axis. So we have the equation for the normal concentration and we have the equation for the back extrapolated concentration also. So what is the next step? Next step is determining the residual concentration. We are applying the method of residual. So residual concentration can be determined how? By subtracting the back extrapolated concentration from the initial concentration. That is CR1 is equal to C minus C back extrapolated. CR1 is equal to C minus C back extrapolated. What is the equation now? CR1 is equal to L e raised to minus alpha t plus M e raised to minus beta t minus N e raised to minus K t minus C back extrapolated, that is M e raised to minus beta t. So we have the final equation as CR1, that is the first residual line, that is equal to L e raised to minus alpha t minus N e raised to minus K t. So the first residual line represents the two exponents, that is a bi-exponential curve that represents the process of distribution and also that represents the process of absorption. That represents the process of distribution and process of absorption. Okay, so this is the bi-exponential curve. Now, graphically, the orange line, the orange graph represents the bi-exponential curve. The orange graph, that is representing the bi-exponential. Initially, the plasma concentration increases by absorption. Later, it decreases by means of distribution. Here, there is no elimination. It's only absorption as well as distribution. Now, we need to determine the distribution rate constant. For determination of the distribution rate constant from the equation, that is CR1 is equal to L e raised to minus alpha t minus N e raised to minus K t for distribution as well as an absorption process. Absorption will be absorption will be completely initially rather than that of the distribution. Absorption will complete initially, even for some more time the distribution will be existing. So the rate constant for absorption will be 0. We can consider it as 0, and that's the term n e raised to minus k at becomes 0. Finally the equation becomes CR1 back extrapolated, that is equal to L e raised to minus alpha t, and taking the logarithm log CR1 back extrapolated, that is equal to log L minus alpha t divided by 2.303. So in the graphically, if you back extrapolated the orange line, if you listen, the orange line, the terminal portion of the orange line represents the process of distribution, and from the terminal face of the orange line, if you get back extrapolated towards the y-axis, so that y-axis there it may intersect, and that is known as the log L. So the equation becomes what? That is CR1, log CR1 back extrapolated is equal to log L minus alpha t divided by 2.303. Okay, so from this we can determine what the rate constant alpha. Previously we determined the rate constant beta, now we got the rate constant alpha, and also we got the y-intercept as capital L here. Now we got the rate constants for the elimination and also the rate constants for distribution. Now this line represents the bi-exponential. Now finally we need to find out what? Find out the absorption rate constant Ka. For determining the absorption rate constant Ka, we need to convert the bi-exponential curve into a mono-exponential curve. So here we have the formula, that is equation, that is CR2 is equal to the second residual line, that is equal to CR1 minus CR1 back extrapolated minus CR1. So don't get confused here. So now only we are going to draw the second residual line CR2. CR2 is equal to CR1 back extrapolated minus CR1. So CR2 is equal to LE raised to minus alpha t minus LE raised to minus alpha t minus NE raised to minus KT. Finally the equation becomes CR2 is equal to NE raised to minus KT. Taking the logarithm, log CR2 is equal to log n minus KT divided by 2.03. So from this equation you can determine the value of Ka. Graphically, the pink line represents the CR2, that is the second residual line. The slope of the residual line is equal to minus Ka divided by 2.03, and the y-intercept is equal to capital N, that represents the capital N, that represents the rate constant, hybrid rate constants for process of absorption. Okay, so this is the end of the presentation. So that's all about the two compartment open model extravascular administration. Okay. So once again rewinding the sessions. So two compartment open model extravascular administration, we have the schematic representation. So initially for exam point of view, when you answer it, you have to draw the schematic representation. You have to write down what is Ka, K12, K21, Ke, and you have to write down this equation also. The other equation also just note down in your notebook, that is dx by dt is equal to Ka xa minus K12 xc plus K21 xp minus Ke xc. Okay, after integrating this equation, converting the hybrid constants and micro constants, we will get this equation. C is equal to Le raised to minus alpha t. The same equation there. You have to explain what is L, what is M, what is N, what is alpha, what is beta, what is Ka. So each and every terms we explain here in point of exam point of view. Next, this graph is only for understanding purpose. Now for determination of the rate constant, first you are going to write down the heading as determination of elimination rate constant. Okay, so for determination of elimination rate constant, the initial phase, the process of absorption and distribution will becomes negligible, becomes value 0. Finally, in the terminal portion of the line or the terminal at the end of the process, there is only elimination. So the term L, M and or alpha and beta becomes 0. The term L and M become negligible. L and N becomes negligible. Finally, C is equal to mu raised to minus beta t. Taking the logarithm, log C bar is equal to mu raised to minus beta t. Then next you can give the heading as from the residual line CR1, that is equal to C minus C back extrapolated. So CR1 is equal to LE raised to, write down the equation. Then you will get the equation for the first residual line as LE raised to minus alpha t minus NE raised to minus KAT, representing by exponential curve. From this you have to split and you have to determine the mono exponential curve. So from this line you are finding out the CR1, that is LE raised to minus alpha t, that is the rate constant for distribution. You will get the value of alpha here, and finally you are determining the second residual line CR2, where you will get the value of Ka. That's it. Okay, so this derivation is not there in your Brahmangar textbook, so write down, clearly write down in your notebook. Everybody please write down in your notebook or wherever you prefer, and send the write it down and take the photo and post it in the Google Classroom. Okay, so that is the task now for everybody. Okay, this test, consider it as an assignment itself. Okay, perfectly how you get out of 10, you should get 10 marks. Okay, in that way you write down from the schematic representation, step by step process of integration. First equation, process of integration. Next equation, give the numbers for the equations and enumerate what are the variables. Everything you enumerate it properly, write down in your notebook, take a photo, post it in the Google Classroom. Okay, accordingly you will get the attendance. That's all. Okay, thank you.